Hello and welcome to today's session, Accelerating Business Critical Oracle Workloads with VMware Persistent Memory using Intel DC Optane PMM. My name is Sudhir Balasubramanian. I am a Senior Staff Solution Architect and the Oracle Practice Lead for VMware. I'm joined by my colleague, Arvind.
I'm Arvind Jagannath, and I'm Product Line Manager at VMware, managing the vSphere platform.
Thanks, Arvind. So essentially, we'll start with a very high-level overview of persistent memory, right? We'll talk a bit about Intel DC Optane PMM, how VMware vSphere platform that's able to consume it, and we'll also look into how performance of business-critical Oracle workloads can be accelerated via persistent memory technologies and the different use cases. And we'll also touch a bit on VMware Project Capitola. So let's get started. All right. So essentially, what we're trying to tell here in the slide is data has been growing at a tremendous rate. So businesses have been going through digital transformations. Applications are changing. More applications need to process data in real time and in memory so the businesses can gather their insights faster. Customers are looking to scale their memory infrastructure. However, as everyone knows, cost becomes very prohibitive. So in addition, customers have to pre-provision memory to scale it to increasing demands. So essentially, VMware has been working with Intel for the last 4 to 5 years on Intel Optane PMM to solve the latency cost trade-off issue. And VMware's persistent memory-based solutions that helps bridge this latency gap. It aims to provide a seamless way to consume memory. So when one mentions the word persistent memory, this PMM layer sits between the NAND flash and the DRAM that provides faster performance relative to NAND flash, but it also provides the non-volatility, which is typically not found in the traditional memory offerings. Essentially, you are marrying right now the performance of memory with the persistence of traditional storage. So persistent memory that can be configured for use in different modes. Essentially, the memory mode. The second mode is the app direct mode, or a combination of the memory mode and the app direct mode, which is referred to as the mixed mode. So with the app direct mode, the PMEM and the DRAM DIMMs, they act as independent memory resources under the direct load store control of the application. What then happens is this allows the PMEM capacity to be used as byte addressable persistent memory that is mapped into the system physical address space, and that can be addressed, accessible, and that is accessibly direct by applications, which is using that with direct load store mechanism via what's known as a persistent memory aware file system. The app direct mode capacity that can also be used as block over app direct. So in this case, what happens is the driver surfaces traditional block storage interface transparent to the application. So there is no any kind of application refactoring or application reworking. So the apps or the operating systems, or essentially the apps, they do not need to be modified. The second mode, which essentially is the memory mode, the persistent memory, they act as a volatile system memory under the control of the operating system, and any DRAM in the platform that will act as a cache working in conjunction with the PMEMs. All right. So let's see how Intel Optane PMM can be consumed by the VMware vSphere platforms. Essentially with PMM in the app direct mode, and that's what our session is focusing on today, the app direct mode, VMware vSphere platform can consume the persistent memory in 2 ways. The first way is storage over app direct, which is also known as vPMM disk. That's the illustration on to the left-hand side of the slide here. What happens here is that the NVDIMM capacity on the host is presented as a local data store. The virtual machine, the virtual disk or the VMDK as it is known, that can be stored on the persistent memory data store, which essentially is backed by the persistent memory DIMMs. And what happens is within the virtual machine, the guest operating system, they will access a regular SCSI device, a block device. And so essentially there are no guest operating system changes required when one uses what's known as the vPMM disk mode of consuming persistent memory. And now on the flip side, when one uses the second way of consuming persistent memory, which is what's known as the vPMM, which means we are able to expose persistent memory as byte addressable persistent memory, essentially by allocating or by adding a virtual NVDIMM component to the virtual machine. So what happens is we are now able to expose the NVDIMM capacity to the virtual machine through a new virtual NVDIMM device. And so the modern guest operating systems, right, they can use it either as a block device or in the DAX mode. So the following use cases in the forthcoming slides, they will focus on using PMEM in the app direct mode directly as byte addressable by Oracle workloads. And we'll look at some of the use cases as well. All right, so let's jump right into the Oracle workload use cases using the vSphere persistent memory backed by Intel Optane DC PMM. All right. So even before we look at the use cases, right? Let's understand. Let's look at some of the challenges with native persistent memory, and let's see how Intel Optane DC PMM in App Direct mode, which is backed by Oracle Persistent Memory Filestore on the VMware vSphere platform, how that is able to address that. So as everybody knows, the native PMEM that operates on a byte by byte basis. It's not by block, which means the data persistence is 8 bytes at any point of time. On the flip side, when you start looking at databases like Oracle, the Oracle database are based on block constructs, which means the block sizes of an Oracle database or table spaces that ranges from 2K all the way to 32K. So if one has to write one 8K Oracle block, essentially one would be writing 1024 times 8 byte PMEM chunks. And while that operation is happening, if there is any kind of power failure, if there's any kind of abnormal condition, what happens is that can result in any kind of fractured or torn block portions of the block, which will contain the old data and other portions with new data, and which means now the database is corrupted. So the solution here is to use the Intel Optane DC PMM in App Direct mode, backed by a feature that Oracle released in 21C, also in 19.12, called the Persistent Memory Filestore on a VMware vSphere platform. And in a nutshell, what the Persistent Memory Filestore or the Oracle Persistent Memory Filestore means, it essentially is a pointer switching PMM file system, and that supports the atomic updates of Oracle DB blocks. And so it provides external interface for mapping and accessing the Oracle database directly in PMEM. All right. So let's have a look at the first use case here. Essentially, the first use case is accelerating the Oracle redo log file performance using PMEM. And even before we go into the use case, let's keep one thing in mind. Any performance data is the result of the combination of hardware configuration, software configuration, test methodology, test tool, the workload profile that's used in the testing. So what we're trying to say here is the performance metrics and the improvement that we get here with this workload, which essentially we ran in our lab, that in no way is representative of any real production workload, which means performance improvements for real workload will be much, much better than what we got in our lab. And by the way, this was by no means any kind of benchmarking exercise. So essentially, we created a virtual machine on ESXi 7.2, 7.0 U2. Operating system was OEL 8.5 UVK. Oracle standalone database version was 21.5. We use Oracle ASM for storage, ASM library for device persistent, essentially making sure that all of the best practices deploying Oracle workloads on VMware was followed. The load generator chosen in question here was LOB, which essentially stands for the silly little Oracle benchmark. And as one can see from these LOB parameters onto the right-hand side of the screen or the slide, the intention was to drive a 100% write-intensive workload with very heavy stress on redo to study the performance improvement using persistent memory. And if we look at the illustration or the figure or the graph, on the left-hand side, we can see that the write IOPS that increased from 61K to 75K. The execute SQL per second, this essentially is a metric that DBAs use to measure how much a workload is pushing in a database, right? Has the workload increased or has it decreased? That's one of the metrics we use. That increased from 29K to 36K. The transaction from second, that increased from 28K to close to 36K. All right. Looking at the same use case one, right? When we start looking at the accelerating redo log file, same use case. When we start looking at what's known as the wait times, essentially the wait time stands for any event that the Oracle database waits at any point of time. We can see onto the illustration on the left, the log file switch completion reduced from 24 to 12%. The overall DB IO wait time that reduced from 20 to 12%. The physical write total IOPS, which is on the right-hand side, that increased from 19 million to close to 24 million. All right, let's take a look at the second use case here, essentially accelerating what's known as the Oracle Flash Cache using PMM file store on VMware platform using Intel DC Optane PMM. In a nutshell, the Oracle Flash Cache, think of it as a level 2 cache for the Oracle memory. So just like in the memory mode, right, we have the DRAM, which is the level 2 cache for actual PMM, right? Or the DRAM could be thought about as a level 5 cache once you go past the level 1, level 2, level 3, level 4 cache on a actual physical server. Similarly, the Oracle Flash Cache is another level 2 cache for the Oracle SGA, right, or the Oracle memory. And so what happens is, anytime dirty buffers get flushed onto the disk, rather than getting it flushed onto the disk, right, once the dirty buffers are written, those buffers are flushed onto the flash cache. So you don't have to go to the disk to reread those buffers or those blocks back. You can go right away to the flash cache, in which case right now, it's not a physical I/O, it's more of a logical I/O. So you're now able to accelerate the performance of Oracle by simply putting that flash cache on persistent memory, right? You're able to accelerate that. And let's have a look at the metrics here as well. So again, in this case, slob was the load generator as well. Looking at the slob parameters on the right-hand side, we can see that the intention here was completely different. The intention here was to drive a 100% read-intensive workload, and this time to study the performance improvement of flash cache using PMEM. And as we can see from the graph here, right, the physical reads blocks per second, that increased from 45K to close to 316K. The read IOPS, that increased from 45K again to 316K. And the executes per second, that increased from 65K to close to 142K, right, per second. So there is an overall increase in the database performance, right, from the execute SQL per second metrics, or even from the physical reads block per second perspective. All right. And let's look at the overall DB IO wait time here. Let's look at the overall IO wait time here. Essentially, as we can see from the chart here, the overall database IO wait time, that reduced drastically from like 38.3% to 0%. The OS CPU sys percentage, that reduced from average of 8.5 to close to an average of 1%. And the best part was the OS IO weight, that reduced from 40% average to 0%, which was very, very impressive. So essentially, you are able to accelerate the performance of the database. The IO wait times came down. The overall DB wait times, it came down. So we were looking at a acceleration of the performance of the Oracle workload, whether it's being whether it was accelerating the read log files, or whether it was accelerating the Oracle Flash Cache in both of the use cases here. And so I'm going to hand it over to Arvind to talk about Project Capitola.
Thanks, Sudhir. Hello, everyone. And let's now talk about a brand new initiative that VMware is doing with Intel Optane Persistent Memory called Project Capitola. In the next few slides, I'll be quickly walking through some of the key value proposition of Capitola, including how it can solve some of the customer pain points. And I'll also talk a bit about the technology. Next, please. Project Capitola brings the advantage of better TCO and scale with a familiar consumption model, which is through vSphere and virtualization. There is no need to engineer software or hardware such as BIOS on the hardware for each application to provide a transparent view of memory. So Capitola can future-proof against technology churn, etc., from various vendors. And it can basically provide a very good TCO reduction. So some of the measurements have shown as much as 20 to 30% TCO reductions with performance close to DRAM. Capitola can solve the density and capacity problem, and thus it can help expand capacity on demand. VMware built a memory monitoring system that keeps track of some of the key memory statistics, such as memory bandwidth, and that includes both DRAM and persistent memory. Capitola can use these stats to also provide faster failure recovery by monitoring memory bandwidth, latency, miss rates, etc. very closely. ensuring that all workloads get a very fair share without any problems such as memory starvation or noisy neighbors or rogue VM kind of issues. The DRS algorithms, which is one of the major parts of vSphere platform, also make sure that some of these stats can ensure further load balancing across the cluster. Next slide. So in this view, we see that Capitola aims to provide a single address space. This will be a sum total of DRAM and persistent memory. Workloads such as VMs and containers, they will be fully agnostic of the underlying memory hierarchy. And the ESX kernel will expose one contiguous memory that can be allocated to all workloads. In the first phase, VMware will provide 2 tiers, and it will tier between DRAM and Intel Optane persistent memory on a single host. This is a fully homegrown software implementation that will be built into the memory management subsystem of vSphere and ESX, as opposed to any hardware modes. The target launch for Capitola will be 2023. This will be available as a software-enabled feature through vSphere enterprise licenses without requiring any separate special SKUs, and thus making customer journey much simpler. Next slide, please. This slide shows the further evolution of Capitola. The vision is to really take this further and support Capitola for a disaggregated, composable, or a pooled memory architecture. Hosts in a cluster will be able to share memory resources. This can further reduce TCO for customers by avoiding over-provisioning. CXL is definitely a part and parcel and will become a major part of Capitola in this architecture. We are also exploring other tiers that can be connected by CXL or by NVMe or Fabric, or even just directly attached PCIe NVMe. Next slide. So in this slide, we cover some of the technology. For simplicity, we are showing tiering using a 2-tier view, but this is extensible to an N-tier architecture as well. On the left, you can see the logical view. This represents what a VM sees, which is volatile memory. On the right, you can see the physical view, which represents where the VM's volatile memory is physically located. vSphere will internally decide the placement of pages in the appropriate tiers based on page activeness and shuffle between hot and cold pages based on certain heuristics. And like I said earlier, the memory available will actually be the sum of all the tiers that Capitola manages. Next slide, please. So let's talk about some of the key takeaways from this session. So digital transformation is leading to larger data sets, and a lot of big data and real-time analytics processing is being performed. Memory is expensive, it is hard to scale and manage, and it requires new software-based solutions. We also saw applications are becoming more real-time, and digital transformation is definitely coming into the picture. And applications benefit from being in memory. Mission-critical applications such as Oracle also benefit from such innovations like Capitola and can thus improve their performance. VMware's Project Capitola and all the PMEM innovations are bringing software-defined scalable memory solutions to address customers and application challenges. And we will continue doing that for today and for the future. Next, please. For more information, please look into the Oracle collateral. So all VMware collateral can be found in the link below.
thank you for the opportunity and thank you for listening to us.
Thanks a lot.